So let's look at the statement of the Riesz representation theorem. It states that if X is a locally compact Hausdorff space and lambda is a positive linear functional on the space of continuous compactly supported functions on X, then lambda induces a sigma algebra B lambda, meaning that here induces means that B lambda can be constructed from lambda. So this is the statement saying that lambda induces a sigma algebra B lambda, meaning that B lambda can be constructed just from the given lambda. And this sigma algebra B lambda contains the Borel sigma algebra Bx. So remember that the Borel sigma algebra was the collection of all Borel subsets of X, which is the smallest sigma algebra generated by the open subsets of X. And so the sigma algebra B lambda that lambda induces, it contains all the Borel sets and a unique measure mu lambda defined on B lambda, such that this positive linear functional lambda applied to f is nothing but the integral of f with respect to this measure mu lambda. Additionally, mu lambda satisfies some extra nice conditions, some other nice conditions, nice properties of regularity, which we call regularity of the measure, which makes it a what is called a Radon measure. So this mu lambda that is induced by the positive linear functional lambda is a so-called Radon measure. So before we come to the proof of the Riesz representation theorem, let's look at the definition of a Radon measure and see some nice properties that Radon measures enjoy on locally compact Hausdorff spaces. So first let me fix some notation. So Bx is the sigma algebra of Borel sets of X. So this is called the Borel sigma algebra. And if mu is a measure on the sigma algebra of Borel subsets, then mu is called a Borel measure. Mu is called a Borel measure on X. So this is the definition of a Borel measure. So now let me go to another page. So if E belongs to B of X, meaning that E is a Borel set, then mu is called outer regular for E if mu of E, so here mu is a Borel measure, so this is a Borel measure, and if mu of E is the infimum of mu of u such that u contains E and u is open in X. So if this equality holds, then mu is called outer regular for E. Similarly, mu is called inner regular for E if mu of E is now the supremum over mu k such that k is a subset of E which is compact. So in this case mu is called inner regular for E. If mu is both inner regular and outer regular for all Borel subsets in X of X, then mu is called a regular Borel measure. This is a regular Borel measure. So if both these conditions, so let me name them 1 and 2. So if both 1 and 2 are satisfied, so it's both outer regular and inner regular for all Borel sets, then mu is called a regular Borel measure. Now another definition, this is about locally finite Borel measure. So a Borel measure mu on X is called locally finite if measure of all compact sets K is finite. For any K compact, we have that the measure of K is finite. So finally we come to the definition of a Radon measure. Radon measure, and this is a measure, a Borel measure mu on X is called a Radon measure if mu is locally finite, mu is outer regular for all Borel sets, and mu is inner regular for all open sets. So here we allow outer regularity for all Borel sets but inner regularity for only open subsets in X. So a locally finite measure which is outer regular for all Borel sets and inner regular for all open sets is called a Radon measure. So what are the examples of Radon measures that we can construct? So of course on RD the Lebesgue measure is a Radon measure, because of course all compact sets have finite Lebesgue measure because they are bounded, so they have finite Lebesgue measure, and we have already seen that for all Lebesgue measurable sets we have outer regularity as well as inner regularity. So in particular, we have outer regularity for all Borel sets and we have inner regularity also for all Borel sets in RD. So not just for open sets, inner regularity holds for all Borel sets, and in fact we have seen that it also holds for all Lebesgue measurable sets. But for the purposes of viewing it as a Radon measure, it is enough to consider outer regularity for all Borel sets and inner regularity for all open sets. And here there is a nuance that if your locally compact Hausdorff space, so let me put this as a remark, that if X is a sigma compact space, locally compact Hausdorff space, and mu a Radon measure on X, then inner regularity for all Borel sets in X holds for mu. So a Radon measure by our definition was allowed only to have inner regularity for all open sets, but in the case of a sigma compact space, so recall that sigma compact space, X is a countable union. It can be expressed as a countable union of compact sets, Aj compact for each J. So when you have a sigma compact space, then inner regularity for all open sets implies inner regularity for all Borel sets. So now we have seen that our Lebesgue measure on RD is a Radon measure. In fact, if you consider alpha, so on X, if you take X to be the real line, alpha is a non-decreasing map, non-decreasing function on R, then the Lebesgue-Stieltjes measure that we have constructed before, M alpha, is a Radon measure. So all the nice examples of measures that we have seen until now, they are Radon measures. Now let's look at another example for abstract spaces, X an abstract space, let's take X and Px as a measurable space with the following measure, with the measure defined as follows. Let us fix a point x naught in X, then we define define the measure mu x naught as follows: mu x naught of any subset E of x, so E an arbitrary subset, then you can define mu x naught of E equals 1 if x naught is in E and 0 otherwise. So this kind of so one can check actually, so let me put this as an exercise, is to check that mu x naught is a measure defined on the sigma algebra of all subsets of x. So in particular, it is if x is a topological space, a locally compact Hausdorff space, then it will contain all the Borel subsets of x and it will be a Borel measure. And now if x is a locally compact Hausdorff space, so by this remark, mu x naught is a Borel measure. This is called the Dirac measure at x naught. So now let us check whether this is a Radon measure. So first is that mu x naught is locally finite, since it is finite. So it's a finite measure, so therefore it is locally finite because it takes only values 0 and 1. Secondly, for outer regularity for Borel subsets, we have the following. So if x naught belongs to E, then mu x naught of E is 1. So for any open set U containing E, we have mu x naught of U is also equal to 1 because x naught belongs to U, and this implies that 1, which is equal to mu x naught E, is equal to the infimum of all mu x naught U, such that E is a subset of U which is open in X, because all of these are equal to, this is equal to 1. So this whole set is the just one number which is 1. So the infimum of just a singleton set is the value of that set. So we get 1. So outer regularity for Borel sets holds in this case. On the other hand, if x naught does not belong to E, we proceed as follows. So of course then mu x naught E equals 0, and now we have to find an open set containing E which does not contain x naught. So our goal is to find an open set U containing E such that x naught does not belong to U. So this would imply that the infimum of mu U such that E is a subset of U and U is open, this is equal to 0, and this would imply that it also satisfies outer regularity when x0 does not belong to E. So let's see how this can be done. So for each y in E, because x is Hausdorff, since x is Hausdorff, we choose an open set, an open neighborhood uy of y such that x0 does not belong to uy. So in fact this is doesn't even require the full Hausdorff condition, it's just T1. So this is the T1 separability axiom. Now we can take the union over y in E of these open sets uy. So this is an open set U, and this contains E because the union is over all points in E, and x0 does not belong to U because x0 does not belong to any of the ui's. So x0 does not belong to U. So this means that our mu x0 is outer regular on all Borel sets in X. Now for inner regularity on open sets, so if E is open in X, now we can divide it in two cases. If x0 belongs to E, then again mu x0 of E equals 1, and now we have to take the supremum of all compact subsets of E and see whether the measures of the supremum of those measures of compact subsets inside E also gives you 1. Now since mu x0 can only take values 0 and 1, then this implies that the supremum of mu x0 k such that k sitting inside E is compact, this is of course less than or equal to 1. On the other hand, we have the compact set, the singleton set x0, this is a compact set, this sits inside E, and mu x0 of this compact set x0, this is equal to 1. So this implies that the supremum is also greater than or equal to 1, which proves that this is in fact so equal to 1. So this implies that mu x0 E is equal to the supremum of mu x0 k such that k is in E and k compact. So this is the case when x0 belongs to E. On the other hand, if x0 does not belong to E, then of course mu x0 E is equal to 0. But now it's obvious that if k is any subset of E, then x0 does not belong to k, and this implies that mu x0 k equal to 0, which means that the supremum of mu x0 k for if you only consider compact sets, then also this is going to be 0. All of these are 0. So we see that it is both inner and outer regular, and it is locally finite. So this means that mu x naught is a Radon measure. Now let's see a non-example. So an example of a measure which is not a Radon measure. So we can take x as Rd, even just R, and mu to be the counting measure. So what is the counting measure? So this is defined on all subsets of R, and this counting measure of a set E is just the cardinality of E. So if E is finite and infinity otherwise. So if E is not finite, it is infinite, and so the cardinality we set it to be infinity. So of course, if you have a compact set, so let's say the set 0 1, the interval 0 1, this is a compact subset of R, but this gives you a value infinity. So this means that it is not locally finite. Not locally finite implies that this is not a Radon measure. So one can even have examples where the measure is finite but not either inner regularity fails or outer regularity fails, but I will not go into these examples. You can look at chapter 7 in Folland's book for those kinds of examples where your measure is finite but it is not Radon, meaning that either outer regularity or inner regularity fails to hold. Okay.